Hello and welcome to this lecture, the fifth in my series on understanding science. Today I'll be talking about the burden of proof, a topic that has come up several times already in passing during my earlier lectures. In short, what is it rational to assume, what is it rational to deny, and what level of proof should we require before we believe unusual claims? Is there ever an occasion where a scientist is justified in rejecting a claim without any further investigation? And if so, then what justification could we possibly give for that attitude? As you can imagine, this topic lies at the heart of much pseudoscience and the majority of conspiracy theories, so hopefully I'm going to put forward a persuasive case for the scientific point of view. Let's get started. Conspiracy theorists and pseudoscientists never cease to develop new tactics for arguing against the results of rational inquiry. However, one or two tactics are absolutely constant weapons in their arsenal, and today we deal with one of those, the tactic of shifting the burden of proof. The situation here that I wish to lay out is that of a claimant putting forward a hypothesis that may disagree with the established scientific consensus. Let's say, for sake of argument, that it's a psychic apologist like Brian Josephson here, who seems to believe that psychic forces are real, and that any research that says otherwise is being unfairly rejected by the major journals. Josephson himself is a highly regarded physicist, a Nobel Prize-winning one nonetheless, who has dedicated his life to the study of condensed matter physics, primarily at the University of Cambridge. So his claim comes at least with the force of plausibility associated with a major intellect of his calibre. But is that enough to make this claim plausible? Should we dedicate millions of pounds and thousands of person-years to investigating these claims? That's a more serious question, because money that goes to psychic research could always alternatively go into researching a cure for AIDS or leukemia. So the initially tempting answer, that we should of course take all claims seriously and investigate them carefully, doesn't seem to be available to us here. There are a great many claims made every day, many of which are completely false. We can't possibly investigate them all, as we simply don't have the resources, so we need to find some way of sorting through all the claims and spending our effort only on those that are likely to be true, or are at least of sufficient importance that their perhaps lesser likelihood is counterbalanced by the exciting gains that would be made were the research to pay off. So it seems like Josephson is onto a winner here. Here's a theory that's proposed by a prominent physicist, and it has potentially enormous implications were it to be true. Yet I still suspect that if I were to do a straw poll of all professional scientists, I would probably find the overwhelming majority would not spend any public money investigating such claims. And I suspect the same is true of many of the general public. So what's going on here? Are we being closed-minded and unfair, or is our response acceptable, even justified? Well, to investigate this matter, let's take a closer look at what it means to gather evidence for a hypothesis, and briefly recap the first lecture in this course on the topic of proof. Let's quickly recap the concept of the spectrum of certainty that I introduced in the first lecture in this course. If you remember, I was talking about how science doesn't really ever dictate truths. Science doesn't deal in absolutes except in very rare occasions. In fact, what science actually does is it attempts to move any hypothesis along the spectrum of certainty, either towards the left-hand side where a theory is more likely to be false, or the right-hand side where a theory is more likely to be true. In practice, hypotheses never actually reach either extreme, but they do tend to get arbitrarily close until the point where the scientific community abandons them as almost certainly false, or accepts them as almost certainly true. We never close down the spectrum, of course. We're always open to moving hypotheses back away from the ends if new evidence comes in, and that's very important. Science is never closed-minded, a topic which I'll return to later in this lecture. So how do we actually move hypotheses around on this spectrum? Well, the answer is that we apply the scientific method, as you learned in Lecture 3. The scientific method is the process by which science progresses, and it consists of building and testing hypotheses in a standardised and rigorous way, with the intention of removing from any process the possible sources of error, including biases. So how does science work? Well, this is moving on to the third lecture in the series on the scientific method, and I don't have time to recap everything I said again, but to summarise, a scientist would test a hypothesis by gathering evidence which could lend weight either for or against that hypothesis. In addition, she would build theoretical models to attempt to explain the hypothesis given known processes that are plausible under existing scientific knowledge, and which explain the hypothesis in as efficient a manner as possible. You remember we talked about Occam's razor, the principle that we should prefer simpler explanations over more complex ones. We also mentioned some philosophers of science, most notably Karl Popper, who proposed the falsifiability criterion for a scientific hypothesis. That criterion said that it's not enough for a scientific theory to be confirmed by observations, but it must also be at least susceptible to disconfirmation, or else it's worthless. For example, the theory that the Earth is only 6,000 years old, but it was created by an omnipotent deity and made to look exactly as it would look if it were 4.6 billion years old. That is, of course, in remarkable agreement with all the evidence we could ever gather. But it's a worthless theory, because there is no measurement that we could ever take that would distinguish that theory from the more natural and commonly accepted theory that the Earth really is 4.6 billion years old. Or similarly, the theory that after we die there is some undetectable remnant of our minds, a soul, that hangs around in some ethereal sense, watching events unfold but completely unable to communicate with the land of the living. That's obviously completely unfalsifiable too, because there is no measurement you could ever take that would detect something that is undetectable. So that hypothesis is worthless too, at least in a scientific sense. What I'm getting at here is that a scientific theory is only of use if it can make testable predictions. And that's another way that we can move theories around on the spectrum of certainty. We examine the theory, work out what predictions it makes, and go out and check if they're true or false. Finally, and of course, we apply Bayes' theorem to the observations we make, and all the data gathered so far that's relevant to the theory in question, to work out whether we have moved it on the spectrum of certainty, and in which direction. So this is all very well, but when does a theory become a fact? Those of you who have been watching these lectures since the beginning will know that there are two ways of looking at that question. The pedantic philosopher or mathematician would of course say never. There's no way we can ever move an empirical theory, that is one that's only provable through observation, to the status of absolute fact. But having said that, it should be fairly obvious that there is a certain threshold past which the certainty is so great that a theory, to all intents and purposes, can be considered to be a fact, and at the other end could be considered false. What is that threshold? Well, I guess it depends on how certain you want to be, and that's something that is decided on a case-by-case basis, of course. I'm tempted to do something a bit unorthodox here and define a level beneath which we can say a probability is zero. What would that level be? Well, it's hard to say, but we need to look at a few fundamental physical scales and see if we could combine them somehow. The Planck time is a natural unit of time, which is the smallest subdivision you can apply to intervals of time, and the universe is around 14 billion years old. And there are something like 10 to the 80 particles in the universe. That's a 1 with 80 zeros after it. So here goes. How unlikely would something have to be that if every particle were tested for this once per Planck time for the entire lifetime of the universe, the chances are it wouldn't have happened yet? Well, that works out as something like 10 to the minus 141st power, or 0.140 zeros and a 1. So pretty unlikely. In fact, I coined the term a while ago that such tiny probabilities should be called zeroid, so close to zero that I'm happy to call it zero, and I'll ignore any mathematician who pointlessly tries to argue otherwise. And of course, in most cases, you don't need anything like this level of certainty, but it never hurts, I guess. What do we need to know to get to this level of support? Well, we're back to the scientific method again here. We need to know the level of evidence in support of your theory. That's pretty obvious. And of course we need to go out and look for disconfirming evidence too. Remember Popper, if your theory can fit any prediction then it's worthless, so a good theory should be capable of disproof, and that's only the case if it makes predictions that could logically be proved wrong. But there's a final step here, because we also need to look at all the alternative hypotheses in the picture too. So it doesn't matter if we have a theory that beautifully fits 100 measurements and has succeeded in passing every potential disproof test that it has ever met. If there are half a dozen other theories on a similar footing, and they all disagree with our first theory, then we can't say that the first theory is unambiguously the strongest contender. Of course, this shouldn't really happen, because a good scientist, on discovering alternative hypotheses to explain the same effect, should try to derive experiments that will help him to decide between them. That is to say, tests that give strong Bayesian support to some theories, but reduce the probability of others. So we can start looking in more depth at the claim of the pseudoscientist or conspiracy theorist that scientists, or even the process of science in general, is closed-minded. What are we to make of that? Well, there are several points to make here, and some of them should be familiar to you already. I've said this before, and I highlighted it a few slides back, but science doesn't dictate truths. It assigns probabilities. It moves hypotheses around on the spectrum of certainty. So if a theory seems extremely certain, it's not that a scientist would cut herself off from all other possibilities, merely that she, through the experiments that she or other scientists have made, has a strong justification for being very confident in the truth of that theory. Take gravity, for example. Now, gravity is one of the most familiar and most reliable theories in all of science. Every day, billions of people are carrying out countless millions or billions of little trials of gravity each. Every time you take a step and don't float off into space, you confirm gravity. Every time you drop a coin or a pen and it falls, you confirm gravity. Every time you look up at the moon or the sun and witness that they're continuing in their orbits exactly as gravity says they should, you confirm the theory of gravity. Fair enough, then, to say that gravity has a lot of evidential support. So what does it mean to be open-minded? Should we be open-minded about the theory of gravity? Should we be willing to accept alternatives? Some would claim that this is exactly what Einstein did with his general theory of relativity, that the differences from the familiar classical Newtonian gravity that we all learned in school are pretty minimal, and certainly not the kind of thing that you would be able to notice with the naked eye. What I mean is, should we be open to the possibility that gravity doesn't exist even remotely like Newton discovered, but in fact gravity varies depending on, say, the colour of the objects being attracted to each other? In my mind, the phrase open-minded means something fairly specific. Or at least, if it is to be considered a virtue and not a huge weakness, open-minded must refer to something like this: that a person is willing to accept any truth, regardless of its provenance, that is, who said it or where they learned about it, regardless of its implications, that is, even if it disagrees with some of our cherished beliefs, or if its truth would cost us a large sum of money, regardless of our prior beliefs, that is, no matter whether we spent the last 20 years of our lives thinking differently, have written papers and books on the alternative, and have publicly declared our belief in an alternative theory. However, I don't believe that being open-minded means that we are obliged to accept any proposition regardless of plausibility, and that's where the conspiracy theorist and the pseudoscientist fall down. Most importantly, being open-minded is not the same as being gullible. Gullibility is the property that some people possess, that they believe whatever they're told, no matter how implausible, because either they put too much trust in an unreliable source, or they're lacking in the necessary critical faculties. Gullibility is definitely not a virtue. It's something that we can quite rightly be praised for opposing. And that's exactly what scientific skepticism as a movement attempts to do. Skepticism, at least in the modern sense, is a middle ground between cynicism on one side, that is, believing nothing unless it already aligns with what you previously decided you want to believe, and on the other side, gullibility. Skepticism is the healthy middle ground, where you require adequate proof for any claims, and you apply the scientific method to attain this. So let's see how this works. A scientist approaches new claims in a well-defined way. Let's step through this with the case that we've been presented with a new claim that seems to go against our established scientific beliefs. First and foremost, there is a very big difference between an evidence-based method for analysing claims and a scientific method. That's not to say that science isn't evidence-based, of course it is, but it's also much more than that, in the same way that Beethoven is, strictly speaking, just noise, but it's also a great deal more than that, as is all music. Science, in the same sense, is a lot more than just collecting evidence. When a scientist encounters a new claim, I think that their thought processes should go something like this. What I'm sketching here is a 3-stage filtering process, which is something like the way I would approach such a situation. Firstly, you have to look at the prior plausibility. By that I mean you would look at the claim and compare it to the theoretical science of which you're already aware. Compare it to the results of previous studies or well-established theories. Look at the plausibility of the evidence with which you're being presented. The theory that gravity depends on colour, as we said before, seems to go against the theory of gravity proposed by Newton, that says that the only relevant variables are the masses of the objects concerned and their separation. So how well tested is that theory? Well, as we mentioned earlier, it's extremely well tested. It's unimaginable that there could be a substantial oversight in the Newtonian law of gravity, at least on the level that we could detect unaided. So here we're at the first filtering stage. You have a certain level of plausibility or implausibility from the prior, by comparing the claims that are being presented to you with what we already know about the world. And at this point, we would look at the evidence that we've been given in combination with that claim and see if it looks sufficient to counterbalance the initial implausibility of the claim. We're not looking for a cast-iron proof here, just merely some indication that there's enough evidence to warrant a second glance. We'll look at exactly how much evidence that should be over the next couple of slides, but for now let's just say that we'd want enough evidence to make it at least plausible that this claim could be true. Let's say that the claim is that the theory of gravity is mistaken. Instead of the colour theory, let's say that gravity in fact only works on organic objects. I think we used this example a few lectures back. Let's say someone attempts to claim that organic gravity is correct, and offers to you the evidence that they threw an apple up in the air and it fell down again. Well, as we learned before, there's a difference between evidence being in agreement with a theory and evidence supporting a theory. Here the evidence is obviously in agreement with the organic gravity theory, but it doesn't really support it, as all we've seen is exactly what happens with standard Newtonian gravity. So given the massive amounts of evidence we have for Newtonian gravity, what we have here isn't sufficient for us to look any further at this new claim. The second stage will be to think about the potential theoretical underpinnings of our theory. Organic gravity has been rejected, so let's introduce a new claim that we have, say, discovered a fossilised rabbit in Precambrian rocks, that is, in rocks that are at least 540 million years old, long before mammals and indeed long before any animals lived on land. While the claim might pass the first test, after all, finding a fossil isn't unlikely. We have millions of them, and we have some Precambrian fossils, though they're quite rare, and rabbits should fossilise just as well as any other animal. So this might pass the first test. The evidence is plausible. But then we have to see how it might fit in with the theoretical picture, and here we run into issues. The rabbit is a relatively recent creature, and our oldest closely related fossils are only about 50 million years old. Also, we know that mammals only evolved around 200 million years ago, and land animals appeared earlier, but certainly after 400 million years ago. So the appearance of a fossilised rabbit in the Precambrian would indeed be an extraordinary find, and would certainly overturn pretty much all of modern biology, chemistry and geology. And those are fields with extremely large bodies of evidence supporting them. So in order to believe that what we're actually seeing here is a Precambrian rabbit, we would expect sufficient evidence to lead us to believe that all our existing knowledge might be wrong. And that's a very tall order. So the Precambrian rabbit might fall at the second hurdle, but we can imagine a claim that might pass that hurdle. A good example here is the 19th century idea that all of space was full of a substance called the ether, in which light propagated. The idea was that sound waves need some kind of medium like air or water or a solid substance through which to travel, so light waves should be the same. This certainly passes the first two hurdles. After all, it's superficially plausible and doesn't contradict any science that was known at the time. There is some theoretical plausibility underlying the idea, and in fact it was proposed because it gave theoretical plausibility to the concept of light as a wave. So, two scientists called Michelson and Morley went out to discover if this hypothesis was in fact true in a very famous experiment. The details of the actual experiment don't matter right now, but their results were negative. They predicted that an invisible ether should produce certain effects. They went to measure those effects, and they didn't find them. So the theory of the ether failed at the third hurdle. David Hume was a celebrated Scottish philosopher and a well-known empiricist. That is, he firmly believed that the knowledge we possess as human beings comes exclusively from our experience of the world, from our senses and the experiences we have during our lives, rather than the competing claim that we are born with much of the most important building blocks of our knowledge already innately available in our minds. One of his most influential works was the Inquiry Concerning Human Understanding, published in 1748, in which Hume lays out his philosophy of epistemology, that is the study of knowledge and how it comes to be learned. The most famous section of this work, at least to non-specialist philosophers, is the 10th section, entitled On Miracles. It seems that Hume's religious beliefs aligned with what we would now call agnosticism, though the term was not coined until many years later. Hume was convinced that miracles did not happen, and he wanted to prove why that belief was warranted, despite the widespread religious convictions of the society of his time, who, of course, punished him heavily for his perceived heresy. Hume's argument has many problems, and is not generally used by philosophers today, mainly because his definitions don't seem to be particularly rigorous or self-consistent. But the overarching form of his logic seems persuasive, and lines up nicely with the theme of this lecture, that extraordinary claims require extraordinary evidence. In fact, Hume's work on miracles is pretty much the basis for that argument. Hume defined miracles as transgressions of a law of nature. This definition also has problems, but let's not look at it in too much detail in case this lecture moves too far from science and into heavy philosophy. So a law of nature is one that has been established by repeated experience, by observation and careful measurement. The law of gravity is an example of this. We test it pretty much every second of every day, as I've already said, and we've never seen an exception to it. That is, we've never found an item that does not behave as gravity says it should behave. So what should we do if we hear a claim that someone has witnessed a miracle? Say that they saw a heavy object, like a grand piano, lift off the floor and float up into the air of its own accord. Well, Hume may or may not have used Bayes' theorem. I'm not aware either way, but the two men overlapped in their careers, as they both lived in the early to mid-18th century. However, what we should do is that we should look at all the possible explanations for the observations that we've made and see which is the most plausible, based not just on how well the explanation fits the observation, but also how well it is supported by prior evidence and how plausible the evidence sounds to us. And Hume's argument, which he put quite nicely, is merely that an anecdote is insufficiently strong evidence to support claims of a miracle. Or, as he put it, no testimony is sufficient to establish a miracle unless the testimony be of such a kind that its falsehood would be more miraculous than the fact which it endeavours to establish. In other words, amongst the possible explanations for the evidence that we've gathered in support of a miracle is the simple possibility that the person who witnessed the miracle is mistaken or lying or confused or just misremembering events. All of these are plausible, all of them happen all the time and have been witnessed to happen many times. In fact, whenever miracles leave enough evidence to permit them to be investigated in any depth, it always turns out that there is some simple, non-miraculous explanation of the event. So it makes perfect sense to assume that this is going to be the case next time we hear of a miracle, until someone provides us with evidence so strong that it can overrule this rather likely alternative. So we're nearly done, but it would be careless of me to finish this lecture without saying exactly how all of this falls out of Bayes' theorem, which you should remember from a few lectures ago. And here it is again in all its glory. Remember, Bayes' theorem says that the posterior, that is, the probability that a given hypothesis is true, given the evidence that we've gathered during our investigation, is equal to the product of the two terms. Firstly, on the far right-hand side, the prior, that is, the probability that we would have given the hypothesis of being correct before we went out to gather this new evidence. And secondly, the support, that is, how much does the gathered evidence provide reason to believe in this hypothesis over and above any other hypotheses that might have been proposed. So what happens when we hear a remarkable or miraculous claim? What does that mean? Well, it simply means that the prior is very low. That is to say, before we go to gather any information, or before we heard the anecdote or read the web page, we would have put the probability of that particular hypothesis being true as very small indeed. And what does it mean to find a claim plausible? Well, it means the posterior should be high. Not necessarily 100%, and of course the value will vary depending on what you're investigating, but certainly you want a posterior of at least a few percent, preferably tens of percent, to make any claim appear plausible. So we have a simple bit of maths here. We want to multiply the very low prior by the support to get a very high posterior. That is, we want the posterior to be very much higher than the prior. So to achieve that, we'd need a very high level of support. And what does that mean? Well, the support, if you remember, is the probability of seeing the evidence that we have, given our hypothesis being true, divided by the background level of seeing that evidence any other way. That is, how much more likely is it to have seen the evidence that we see if our hypothesis is true than if it isn't? We might grant that our new hypothesis would be certain of providing this evidence, which is very rarely the case. After all, say, crop circles might be consistent with landing alien spacecraft, but it's hardly true that all alien spacecraft would definitely land in coalfields and definitely leave such evidence. But even if we set P of E given H equals 1, that is, the probability of getting our evidence if our hypothesis is true is absolutely certain, then we still have the situation that Hume proposed, namely that the background probability of our evidence happening under all possible worlds, that's P of E at the bottom there, would need to be roughly the same size as our prior. That is, the more unlikely our event is to have occurred naturally, the more unlikely we should expect the evidence to be on a natural hypothesis. That's quite a large argument to accept all at once. Let me try to put it another way. We're looking for evidence that is extremely strongly in support of the miraculous claim, but which is extremely unlikely on any other theory. That's what it means for evidence to be strongly in support of a hypothesis. And the more unlikely the given evidence is on any other theory, the stronger support it gives to the miraculous claim. But anecdotal evidence, as we've already said, isn't very unlikely at all. In fact, the world's chock full of anecdotal evidence of all kinds of miraculous claims. And the alternative medicine literature is full of claims of miraculous healing medications that can cure you of pretty much any disease, and all are, of course, 100% natural. Faith healers claim to be healing people of a serious disease left, right and centre, and all manner of charlatans prey on the grief of the recently bereaved by claiming that they can communicate with their deceased relatives, albeit very suspiciously vaguely and ambiguously. So what is the burden of proof? Well, it's just this. It's the support component of Bayes' equation. If that's not high enough, then I'm under no obligation to take your claims seriously. None. And it's not a matter of being closed-minded. It's a matter of simple, logical probability theory and common sense. So in this lecture, I think I've given a review of what I've already said earlier in this series about the concepts of proof and evidence and the application of Bayes' theorem, and the conclusions that I've made are as follows. Firstly, it's impossible for any one human being to dedicate all their effort on each and every claim that they come across. In fact, it's impossible for any one human being to dedicate any more than a trivial amount of time to the vast majority of claims that they encounter. Consequently, there must be some way for accepting or rejecting a subset or even the majority of all claims with little or no further research before reducing the total number of claims that you have to investigate to a more manageable number. And I believe that this process should be iterative. That is, you should devote an increasing amount of effort in investigating a decreasing number of claims, ones that have passed earlier less rigorous scrutiny and are consequently worthy of a more thorough approach. Secondly, I argue that intuition and closed-mindedness were very bad ways to approach this filtering process that must occur, because they have extremely high error rates and make it unacceptably likely that you'll discard a truth or accept a falsehood. Thirdly, I argue that the best way we have of sorting truth from falsehood is the scientific method, and that it is possible to apply scientific findings to this process, even without new experimentation, purely by relying on the results of existing experimentation and theory that are relevant to the case in hand. Fourthly, and finally, I laid out the application of Bayes' theory to the analysis of plausible and implausible claims, deriving the general rule that, as Hume first investigated and as Carl Sagan rather memorably put it, extraordinary claims require extraordinary evidence. I illustrated why I believe that this is a valid and rational maxim to live by, and I countered a few of the various criticisms that have occasionally been raised against it. So that's all for now. I'll put the notes for this lecture up on my blog at frame.net, where you can also follow the other many and varied projects that I'm working on, and you can leave your comments and questions. In particular, if there's an aspect of science that you don't understand, then drop me a note, and I'll see if I can produce a presentation on that very topic. The next lecture will be on the subject of conspiracy theories, and how human psychology mixes with pseudoscience to produce sensational headline-grabbing claims. Thanks very much for listening, and I'll see you next time.